Welcome to the video lesson for section 8.7, probability. Let's get started. To begin with, we have some terminology. Our first term is experiment. So an activity with an unpredictable result is called an experiment, which means pretty much every activity or every problem we're going to be doing within this section is going to be considered an experiment. Within each experiment, the results of each experiment is going to be called an outcome. So whatever happens within our experiment is an outcome. All of those outcomes together create your sample space, or all of the possible things that could happen. And then the number of outcomes is going to be denoted by n of s, where we're going to be counting the total number of things that could happen. For our first example of an experiment, we have flipping a coin. Your sample space is going to be comprised of all the things that could happen. So if you flip a coin, it could come up heads or it could come up tails, which is going to be our sample space, again being heads or tails. And then for the number of things in your sample space, we're going to count the total number of outcomes we had, which was 2. So the number of terms in our sample space is 2. With our second example here, we have tossing a die. So if we roll a die, again, we want to think about what could happen. We could roll a 1, a 2, a 3, 4, 5, or 6, and that's going to make up our sample space. Again, all the total possible outcomes. If we count the number of outcomes, we have a total of 6, so there's 6 things in our sample space. While a sample space is everything that could happen, a subset is a smaller portion of that. So for a subset of a sample space, we're going to call it an event. We're looking for something specific to happen. The number of outcomes in the event is going to be denoted by n of v, where we're going to be counting the total number of outcomes within our event. For our first experiment, we're going to say that we're flipping a coin. The event that we're looking at specifically is getting a heads. So how many ways could we flip a coin and get heads? There's actually only one way. We get heads. So this means the number of outcomes within our event is going to be 1. If we switch our experiment to tossing a die, then the event we could be looking for is getting an even number. So if we toss a die, how many ways can we get an even number? There are 3 different outcomes. We have 2, 4, and 6. So the number of outcomes in our event is going to be 3. If we're tossing a die and instead we want to get a 3 or higher, so in this case including 3, then we could get a 3, 4, 5, or 6, which means we would have 4 outcomes in our event. If we're drawing a card from a standard deck, we want to get an 8. How many different ways could we get an 8? There are 4 different 8s. We have the 8 of clubs, 8 of hearts, 8 of diamonds, and the 8 of spades, which means, again, our event is going to have 4 outcomes. And then if we're flipping 2 coins, and we want our event to be that we get at least one of those coins to be heads, how many ways could that happen? Well, we can get both heads. We can get heads, then tails, or we can get tails and then heads, which means that our event is going to have 3 different outcomes. What we're going to be doing now is looking at the number of outcomes within our event and using that with the number of outcomes in our sample space to then create a probability. Coming now to our definition of probability, if we have an event E from a sample space of equally likely outcomes, meaning everything has the same probability of happening, then the probability that the event happens is equal to the number of outcomes in E divided by the number of outcomes in your sample space. And it's important to note that for your probability, it's always going to be a number that is going to be between 0 and 1. We have 2 properties to kind of introduce now. One of them is going to be the impossible event. So if the number of outcomes in event E is equal to 0, that means its probability is also going to be 0, so it's impossible for that event to actually happen. If the number of outcomes in your event is equal to the number of outcomes in your sample space, then that means your probability must be 1, and that makes the event certain, so it's always going to happen. We have a couple examples to kind of highlight these properties. So to begin with, we have a 6-sided die. One of the questions is, what's the probability that you roll a 10? Well, there are no 10s on a die, so that means that there are 0 ways to roll a 10 out of the 6 total ways to roll your die. So we have 6 over 10 as our probability, which means our answer is 0. So this is an impossible event. If we change that question and we want the number that we roll to be less than 10, well, all 6 numbers on your die are less than 10. So the number of outcomes in your event is 6, and the number of outcomes in your sample space is 6, so this is going to be a certain event, or it's always going to happen. And then for your last example, the probability that we in fact roll a 5, there's only one way to roll a 5, so the number of outcomes in that event is 1, divided by the 6 ways to roll your die, giving us the probability of 1/6. All right, for this example, we're going to find the probability of getting exactly 2 heads if we have 3 coins that are thrown. In order to kind of do this, I like to build up my sample space for the entire experiment. So I have in front of you all the different outcomes for flipping 3 coins. And note that it kind of matters the order things happen. So we have the first coin is heads, second coin is heads, third coin is heads, and so on. And we have a total of 8 different outcomes within our sample space. We want to know of these outcomes, which ones have exactly 2 heads. So we have 3 different outcomes that have exactly 2 heads, which means the number of outcomes in our event is going to be 3, whereas the number of outcomes in our sample space is 8, giving us a probability of 3 over 8. Now for our next example, we want to know if 2 dice were thrown, what's the probability of getting a sum of 7? There should be a sum of 7. So the 2 dice add together to equal 7. If we look at that event specifically, we have 6 different ways we can get a sum of 7. So we have a 1 and a 6 or a 6 and a 1. And these are different because we have the first die and then the second die. Or we have, again, first die and second die. So we can see those values are different. We also have 2 and 5 or 5 and 2. And then 3 and 4 or 4 and 3. So again, there are 6 outcomes in our event. For rolling 2 die in general, there are 6 outcomes for the first die and 6 outcomes for the second die. So using our combinations, we should have a total of 36 different outcomes for our sample space, which means that for our final probability, if there's 6 outcomes in our event and 36 outcomes in the sample space, then we should have a 6 over 36 or a 1 out of 6 chance that we can get a sum of 7. By rolling a die again 3 times, the question here is what's the probability that all 3 rolls are in fact a 4? So for our first roll to be a 4, there is going to be a 1/6 chance that that happens because there's 1 4 on the die and then there's 6 total numbers. For our actual experiment, we want to roll 3 4s, so we're going to have that probability happen 3 times. We have the first die, the second die, and the third die, which means they're all going to get multiplied together. So we have 1/6 times 1/6 times 1/6, or 1 out of 216. All right, for our next example, we have a random number generator that is going to generate numbers from 1 to 20. So the question here is, what is the probability all 3 numbers are in fact less than 7? So if we look at one number being less than 7, we have 7 different numbers. So we have 1 through 6, which means that probability is 7 out of 20. We're going to repeat this 3 different times, though, because we want to draw or generate 3 different numbers. So we have 7 over 20 for each event. Repeated 3 times gives us 7 over 20 times 7 over 20 times 7 over 20, which is 343 over 8,000. One thing to note here, guys, for our final answer, I'm going to kind of want one of 2 different things. All right, here we have 2 coins being tossed. The question is, what's the probability that at least one comes up heads? So again, we want to build our sample space for our experiment. We have 4 different ways this event could happen. So we have heads, 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 tails, tails, heads, or tails, tails. Of that sample space, our event is getting at least 1 that is heads. So I could have 2 heads or 1, and there's 3 ways for that to happen. So the probability of our event then is going to be 3 out of 4. For our next example, we're drawing cards from a deck of 52. We want to know what is the probability that the card drawn is a face card. So for our face cards, that's going to be a jack, a queen, or a king. Looking at your sample space, again, there are 52 total cards. Of those 52 total cards, we can see that we have 12 different cards that are going to comprise our event. So for our probability, we have 12 over 52 as our final answer. For the union of 2 events, if we have A and B as 2 different events, then the union, symbolized as A union B, is the event that A or B happens. And the important thing here is it consists of either A happening, or B happening, or both A and B happening. Let's look at an example here where we have a deck of 52 cards. So in our standard deck of 52 cards, we want to list the outcomes for the event of getting a club face card or getting a jack. So we have 2 separate events happening, but there is some overlap where we could have a face card that is also a jack. If you look at our 2 events, we could see that event A, getting a club face card, would be the 3 outcomes of a king that's club, a queen that's a club, or a jack that's a club. Getting just a jack, we have the 4 different jacks, so jack of clubs, diamonds, spades, or hearts. But we do have some overlap here. So we could have one happen, the other happen, or because of the overlap, we could have both. So those 7 different outcomes comprise our event of getting a club face card or getting a jack. If we compare the union with the intersection, we see here that if A and B are events, the intersection, written as A intersection B, is the event A and B. So this is only going to consist of the events that happen to both A and B at the same time. So whereas the union is A or B or both, the intersection is just A and B. If we go back to our last example with our standard deck of 52 cards, we're going to change our event now to be getting a club face card and getting a jack. If we list our different events, we have getting a club face card, which is again the 3 club face cards. Then we also have getting a jack, so we have the 4 jacks. For an intersection, it is only where these 2 events overlap. So in this case, we would have just the outcome of getting a jack that is a club face card, and that's going to be the only outcome in our event. All right, that leads us to our equation here. If we have A and B that are different events, then the probability of A or B, or the union of A or B, is going to be our following formula. So the probability of union is the probability of A plus the probability of B minus the intersection of A and B. I can see it's kind of color-coded here, but essentially the union is all 3 sections. A is going to be the red and the purple. B is going to be the black and the purple. So we have to subtract that purple because it gets counted twice. So we subtract one of them to end up balancing our equation. Let's go ahead and apply this. All right, for our example here, we're again drawing a card from a deck of 52. We would like to know what is the probability the card is a red card or a queen card. So we're going to go ahead and look at our sample space. We can see that getting a red card, we have all of these different outcomes. There are 26 total outcomes that are red. Getting a queen, we have 4 different outcomes. If we were to add these together, we'd have to be mindful of the overlap here. So if we interpret our chart here, we can see that the probability of getting a red card and a queen, so that it's a red queen, is 2 out of 52. That's our overlap here. And then we have the probability that the card is a red or a queen is the same as the union. So if we apply our formula, we have that the probability of getting a red card or a queen is getting a red plus getting a queen minus the red queens. So we have 26 over 52 plus 4 over 52 minus the overlap, which is 28 over 52 or 7 over 13. So again, we're just showing here that we're subtracting the overlap because it gets added once for the red cards and a second time for the queens. So we have to subtract it at the end to balance out what we've done. All right, for next example, we have a card being drawn from a standard deck. We want to know what is the probability that it is a spade or a face card. All right, so if we think about a deck of cards, then there are 13 different cards that are a spade, and then we have 12 cards that are a face card. For the overlap, we want to know how many cards are a spade and a face card. So we have 3 of them, the jack, the queen, and the king. As we go ahead and look at our formula, I can plug in my pieces because I know all the information. So I'm going to plug in my 13 over 52, my 12 over 52, and then subtract off that overlap. And when we do, and we simplify, we end up getting 11 over 26 as our final probability. Continuing with our standard deck, we want to know what is the probability that a card drawn is a 4 or a red card. So we have 2 events, getting a 4 or a red. If you look at your probabilities, there are 4 4s in our deck, the 4 of each suit. There are 26 red cards. And then for the overlap, there are 2 4s that are red, the 4 of hearts and the 4 of diamonds. So plugging those values into our formula, you can see that we have 4 plus 26 minus 2, which is 28 out of 52, which will simplify to be 7 out of 13. Occasionally, we have events that are called mutually exclusive. Events that are mutually exclusive have no intersection. So if we had event A and event B, they have nothing in common. When we have mutually exclusive events, we see our formula is a little different. We have the probability of A or B is just equal to A plus B. And again, that reason is because there's no overlap, we can see we don't have to subtract anything off because nothing gets counted more than once. We have the red portion and then we have the black portion. We're not counting any section more than once, so our formula doesn't need to account for that. All right, for our example here, we have a card again drawn from a deck. We would like to know the probability that the card is a king or a queen. So looking at our different probabilities, we can see that the probability of a king is 4 out of 52. The probability of a queen is also 4 out of 52. And just to highlight that our events are in fact mutually exclusive, the probability of getting a king and a queen is 0 because there's no card that has a king and a queen at the same time. So when we plug these into our formula, we can see that we're just doing A plus B. I'm demonstrating that we're subtracting 0 here, which is another reason why we don't need to add this part in when our events are in fact mutually exclusive, because our answer again is just A plus B, which is 8 out of 52 or 2 out of 13. Here we have a visual representation. Our question is the probability that the card is a spade or a club. We can see we have the event of being a spade here with all of the outcomes for our spades. We also have the event of being a club, which is all of our outcomes of having a club. And there is actually no intersection because there are no cards that are spades and clubs at the same time. So when we go to find our probability, we can say they are in fact mutually exclusive, which means I can simply add together the individual probabilities and I get as a final answer 1/2 for the probability of getting a card that is a spade or a club. In addition to mutually exclusive, we have events that are independent. Independent events are events that occur and have no effect on the likelihood of each other. So for an example, if I'm flipping 2 coins, I can confidently say that the first coin flip coming up heads and the second flip coming up tails are independent because the first coin flip has no effect on the second coin flip. Because of this, we have the following formula that the probability of A and B is equal to the probability of A times the probability of B for independent events. All right, for our example here, we're going to draw 3 marbles from a jar with replacement, and that with replacement is key because it guarantees that our events are in fact going to be independent. So we want to know if there are 3 yellow and 4 blue, what's the probability that we draw 2 blue and then 1 yellow? And we're drawing them in this order. So the probability that our first marble drawn is going to be blue is 4 out of 7. 4 because that's our event and 7 because that's our sample space. So we have a 4 out of 7 chance that the first marble is going to be blue. That marble is put back in, which means that again our events are in fact independent because I have the exact same probability of drawing my second marble and it also being blue. And then for my last marble, I'd like it to be yellow. So this time it's going to be actually 3 out of 7. When we multiply this all together, we get a final probability of 48 out of 343. And for our final terminology here, we have the idea of the complement. So if A is an event, then the probability of not getting A is going to be 1 minus the probability of getting A. And the not getting A notation here, we have a little apostrophe above our event. This is known as a complement. So the complement is essentially the opposite. If I knew the probability of getting something was 40%, then the complement of that would be 1 minus or 60%. And sometimes it's easier to calculate the opposite instead of calculating what we actually want. If we look at an example here, we can see a die is tossed. We want to know what the probability of getting a 2 or higher is. So there's not a ton of outcomes in our sample space here, but we could think about the opposite of this. So the opposite of getting a 2 or higher is getting something less than a 2. And there's only one thing we can get that's less than a 2 when you're rolling a die, and that's a 1. So we can think of, it's easier to get the complement, which would be getting a 1. I can take that 1 out of 6 and subtract it to end up getting my final answer, which would be 5 out of 6. So again, we kind of want to rethink this. Instead of getting a 2 or higher, we want to know what's the probability of not getting a 1, which would be 1 minus 1 out of 6, which again is just 5 out of 6. Here we have a visual representation of the idea of a complement. So again, if A is an event, then the complement of A, which is written as a complement, is everything that is outside of A. So if my event is getting 1 head and 1 tails, that would be A, right? I would have either outcome that has 1 head and 1 tails. The complement of A, again, the A apostrophe, that complement, is the opposite or the outside. So I could see here that that's going to be comprised of getting 2 heads or 2 tails. So if I wanted to list the outcomes, if I know that these are the 2 outcomes of A, then the complement is going to have the other 2, again, the 2 heads or the 2 tails. All right, guys, that does it for our notes for this section. Go ahead and get started on the homework, and good luck.